All right, we're going to talk about exponential functions now. So we want to start that discussion by sort of comparing exponential functions to linear functions. So when we see an exponential equation, we'll notice it by the exponent being the variable. So there will be an exponent in the variable. The variable will be in the exponent. And so if we look at what happens with exponential growth compared to linear growth, you can kind of think of exponential growth as doubling every time or being multiplied by 3. Basically, exponential growth is multiplication, whereas linear growth is addition. You're adding 2 every year or something. So you can see that exponential growth is going to be much, much faster than linear growth. And when you think about it, wanting a growth factor or a multiplication problem. So an exponential function looks like a times b to the x, where a is some non-zero number, and we think of it as the initial or starting value of the function. You can think of it as the y-intercept. And then b is a positive number not equal to 1. So what we're going to notice is that when b is bigger than 1, we call it growth, and the function goes up kind of curvy because it gets faster and faster. When b is less than 1 but bigger than 0, we call it decay, and the function is coming down. So if you're multiplying by a number bigger than 1, it's going to grow. If you're multiplying by a number between 0 and 1, it's going to decay. And that's how we'll know what the picture kind of looks like. So let's look at these two examples. For each of the following, think about whether it's an exponential or a linear function. So remember, exponential, you're multiplying by a particular amount every time. Linear, you're adding. The average annual population increase of a wolf pack is 25 wolves. So every year it goes up by 25 wolves. So I'm not multiplying by 25, I'm adding 25 wolves to the pack every year. So this is a linear function. A population of bacteria decreases by a factor of 18 every 24 hours. So that means I'm going to divide by 18 every 24 hours. So this is exponential. And this is decay because it's getting smaller. The value of a coin collection has increased by 3.25%. To find a percentage, we multiply again. So this is going to be exponential growth. And then for each training session, a personal trainer charges his clients $5 less. So he's not multiplying by 5, he's just taking away $5 from the cost every time. So linear. Okay, here are examples of two exponential functions, 3 times 1.8 to the x and 2.1 times 0.4 to the x. And it wants us to determine, are they growth or decay? And what's their initial value? So if you remember, this a in the front is the initial value. So this initial is going to be 3. This initial is going to be 2.1. And that works whether it's growth or decay. To determine growth or decay, we look at that number inside the b. So a times b to the x. A is the initial value. B is the growth or decay. If b is bigger than 1, it's going to grow. If b is less than 1, it's going to decay. So in this one, b is 1.8, so that's a growth. In this one, b is 0.4, so that's a decay. So how do we evaluate exponential functions? So here's a function, 5 times 3 to the x plus 1. So this whole x plus 1 is in the exponent up there. So if I want to find f of negative 3, I'm going to do 5 times 3 to the negative 3 plus 1, or 5 times 3 to the negative 2. You can put that in your calculator, 5 times 3 to the negative 2. 5 times 3 to the negative 2 gives me 5/9. F of 0, so I'm putting 0 in for that exponent again, 3 times 0, 3 raised to the 0 plus 1. So 5 times 3 to the 1. 3 to the 1 is 3. 5 times 3 makes 15. The population of India was about 1.25 billion in the year 2013, with an annual growth rate of 1.2%. So they got an equation from that. Notice that that 1.25 was my initial amount, and then this 1.2% is in here as a growth amount added there, where t is the number of years since 2013. To the nearest thousandth, what will the population of India be in 2031? So t is going to be 2031 minus 2013 because I'm starting in the year 2013. So that's 18 years. So in my equation, I'm going to plug in 18. So 1.25 times 1.012 to the 18. I'm going to put that in my calculator. 1.25 times 1.012 to the 18th gives me 1.549. 1.549. But remember, this was in billions of people. So billion people.